7.2, transformations of exponential functions. So we're going to see some things that we've seen before um, using transformations. So our general form is y equals a, c is still the base, to the power of b, x minus h plus k. We're going to use that same information that we have in the past two units. A is a vertical stretch. A is negative, we reflect on the x-axis. B affects a horizontal stretch by a factor of 1 over b. B is a negative, reflect on the y-axis. H, horizontal translation. If H is positive, it's to the right. If H is negative, it's to the left. So if I had x plus 3, well, it's supposed to be x minus h. So here, h would be negative 3, and we would move to the left. Okay, so that's just like in Unit 1 and Unit 2, transformations. And finally, K affects vertical, that's how we remember it, translation up or down. Let's try a problem. A cup of water is heated at 100 degrees and then allowed to cool in a room with an air temperature of 20. The temperature in degrees is measured every minute as a function of time, m in minutes, and these points are plotted. It's found that the temperature of the water decreases exponentially at a rate of 25% every 5 minutes. So here we've plotted the data, we've been given this graph, and our task is to come up with the equation using this base right here. Okay, the one thing I can do for certain is I can tell you what the base is, what C is. Okay, so it says it decreases exponentially at a rate of 25%, so 75% is left. So here's my base function. Okay, so it's going to look similar to this, only we've done some transformations and translations. Okay, so first thing we're going to change is it said it's measured every 5 minutes. So we're going to take the time measured and divide it by 5 as our exponent. Another piece of information that we know is that we are in a room temperature of 20. So the temperature isn't going to go down to 0. It is going to stop at 20. So you can kind of see there's a line 20 there, like a horizontal asymptote. That is going to give me my vertical translation. It's like you took a normal exponential graph and it's moved up, and it has moved up 20 units. So we're going to go plus 20. Okay. Next thing I want you to look at is right up here. Okay, where it crosses the y-axis. The y-intercept is almost always 1 for exponential, for a base exponential function. But here it's at 100, so it's obvious to me that there must have been some sort of vertical stretch. It has been stretched out to bring it all the way up to 100. And we need to find out how much it has been stretched. So we're going to do that by using the point 0 and 100, and putting it into our function here. We know that there's some a value. We want to figure out what that a value is, so we're going to sub in the values 0 and 100. So 0 goes here, and 100 is the value of the function at 100 is the value of the function at 0. Okay, so 100 equals a times 0.75 to the power of 0 over 5 plus 20. Anything to the power of 0. 0 divided by 5 is just 0. Anything to the power of 0 is just 1. So I have a times 1. 100 equals a plus 20. To get a by itself, I subtract 20 from both sides. I get my a value to be 80. So my final function, going back here, is going to be y equals 80 was my a value times 0.75 m over 5 plus 20. Where did that m over 5 come from again? Up here, it says measured is measured every minute as a function of time. It decreases exponentially every 5 minutes. So every 5 minutes is why we had to take the time and divide it by 5.